Okay, so let's get back to what we were talking about here in chapter 4 in terms of reactions. Reactions are what chemistry is all about, right? Making and breaking bonds and understanding them so we can utilize chemistry to do things we want molecules to do. And we need to have a really good understanding of how molecules behave. And in order to understand how molecules behave, we have to have a good understanding of the structure of the reactants and the intermediates along the way. So we were talking in detail last time about this particular reaction, the addition of something like a mineral acid like HBr or HCl to a double bond with the functional group of the double bond being the nucleophile in this reaction in this first step, the proton being the electrophile. And we know from a lot of experimental studies that the reaction proceeds by a two-step mechanism, as we've talked about before, and I've drawn the reaction energy diagram to remind you of those details. So just to highlight a couple of things in this reaction, that there's one step in the reaction is the slowest step. I think people actually did pretty good on this question on the problem, actually, identifying the pieces of the energy diagram. But this is the highest activation energy, and so it's this first step which actually sets the overall rate of the reaction and the direction the reaction can go. And it's important to understand that first step and the intermediate that's formed, the carbocation, okay? Because when we start observing these reactions in something other than ethane, we see that the reaction has some very specific pathways which it undergoes to form selective products. So if you think about the details of the mechanism and how the reaction could proceed, in this case when we have double bonds on the end of a chain or somewhere that's not symmetric anymore, the two ends of the double bond are different. So which side does the proton go on? Which side does the bromine go on? It's a good question. What directs that and what influences the product formation? Okay? An understanding of the intermediate is very important to do this because we see that the reaction is very selective. It only goes in one direction to give one of the possible two products in these examples. Okay? So then you have to ask the questions, why does that happen? Why is it selective? And can we explain how that's happening? So to remind you, Markovnikov rule basically put into words this empirical observation that when you add HBr or HX to a double bond, the hydrogen goes on the carbon with the most hydrogens and the halide goes on the carbon with the least hydrogens, or the more substituted carbon. That's just a description of what's observed. That doesn't say why. It's predictive. You could remember this rule and be able to apply it, but it still doesn't explain why it happens, right? And that's what we want to understand as chemists. Why does it happen? Because we might be able to apply that information to other cases besides HX addition. Okay, so if we take a look at this intermediate, we see that the intermediate along the way, the first thing that's formed in this slowest step is a carbon with a plus charge, a carbon with an empty orbital. Okay, it's an intermediate. So understanding the nature of that intermediate that's formed is critical for determining the pathways for the reactions and the possible pathways. So when we think about a carbocation intermediate, we need to understand the structure. As we talked about before, when we look at the hybridization and the shape of atoms when they're bonded in molecules, we can see that when an orbital is empty, it's not taking up any electronic repulsion space, if you will let me use that term loosely. So in order to get all of the bonds that have electrons equally spaced around the carbon, it adopts an sp2 hybridization. So the plus charge, or the empty orbital, is an unhybridized p orbital. That gives a flat shape to the molecule. It looks something like this. And carbocations are planar, just like a double bond that we would, excuse me, that we would also see when we have pi bonds. They have to use the same p orbitals. Okay, so everybody understands the structure of what the carbocation looks like. sp2 hybridized with an empty p orbital where the plus charge is. Okay. Well, when we have double bonds which are unsymmetrically substituted, and we add a proton to that, we could form two different carbocations with different substitutions. And what's been observed, and this is now leading towards a better explanation of what we observed in those reactions, is that the more substituted the carbon that has the plus charge is, the more stable or lower in energy it is. Okay? The higher degree of alkyl substitution. So something with no hydrogens, a methyl group, is going to be the least stable, the highest energy type of carbocation. As you put more and more alkyl groups, which I've just represented here just as the CH3s, that stability or energy of the carbocation goes down. The stability increases, the energy lowers. Okay, so the most stable carbocation substitution would be a tertiary carbocation, a carbon with 3 alkyl groups attached. Okay, so think about that for a minute. The reason for this stability has to do with the electrons from adjacent bonds providing electron density towards that empty carbocation. So it's not really neutralizing the plus charge, but it's spreading it out more across the molecule. Okay, so electron density from bonds are helping to neutralize, not helping to alleviate the energy of the plus charge. And I've shown that here. We talked a little bit about this last time. The terms that we use to describe two different effects that help to stabilize the plus charge are inductive effects, in which electrons in the signal bonds, the plus charge polarizes the bonds. It's kind of like thinking about the carbon as, when you have it as a carbocation, it's a lot more electronegative now than a carbon that has 4 bonds with all electrons. Okay? So essentially the carbocation has become more electronegative and it polarizes the signal bonds between it. That's one effect. That's an inductive effect, we call that. The other effect is when you have a case where the p orbital of the double bond is aligned with one of the CH bonds or some other single bond on the adjacent carbon. Now with an empty orbital and a bond with electrons, that's a positive interaction where the electrons help alleviate the plus charge. This is what we refer to as hyperconjugation. Okay, so that's the other term that we use to refer to the stabilization of carbocations by hyperconjugation. So this is just sort of a graphical picture on the left. On the right is actually a calculated molecular orbital using quantum calculations to show how the electrons are distributed. You can see that the p orbital on this carbon, which is right here, that's the carbocation, that some of the electron density that's over here in this CH bond is helping or interacting with that p orbital. That's a calculated picture, but it tells you how that plus charge is spread out and somewhat alleviated. That's what we refer to as hyperconjugation. So if you have one of these, it helps alleviate the plus charge. If you have 2 alkyl groups, then you would have 2 sides doing hyperconjugation towards the carbocation. If you have 3 of them, the most substituted carbocation, then you would have 3 of those bonds helping to alleviate the plus charge. Yes, question?
Wouldn't the charged carbocation or positively charged carbocation be more electropositive?
The carbon is more electronegative, meaning it's pulling electrons towards it because it is positive. Okay. Yes, the carbon, it's becoming, okay, now we gotta split hairs on terms. Yes, it's a more electropositive atom, but it's increased strength of electronegativity for pulling it. So careful not to confuse those two terms. I know it sounds counterintuitive. Okay, so let's think about that for a minute. More substituted double bonds, or more substituted carbocations are more stable. So if you have a reaction of an addition of a proton, the first step forms a carbocation, the intermediate energy for the two possibilities will be different. So in this energy diagram, I'm showing you two possible pathways for an unsymmetric double bond. In this case, I'll draw it a little bit larger for you. R is an alkyl group. Okay, so that's an alkyl group. If you add the hydrogen to the N carbon, you'll get this transition state and then this intermediate on the left. And if you add the hydrogen to the carbon that's on the inside of the double bond, it puts the plus charge out on the end to form this carbocation, which is on the right. Okay. This one happens to be a primary carbocation. This one is a secondary carbocation. So the more substituted one is going to be lower in energy. Okay. And the energy of that intermediate affects the energy of the transition state to get there. So the overall activation energy, sorry, I just deleted that. Okay, so the overall energy of activation, or the barrier you have to get over to get to the more stable intermediate, is less than the energy it would require to get to the less stable intermediate. Okay. That's why the reaction chooses one path over the other. It's selective for the pathway which is less energy than the pathway that's higher energy. And in those cases that I showed, those examples, we saw only a single product. That is the substitution to form H on the most substituted carbon, Br on the, I'm sorry, H on the less substituted carbon, Br on the more substituted carbon as the only product. That means the difference in energy between here and here must be great enough that it's completely selective. It doesn't go into that pair pathway at all. Okay, so now we see this reaction. We understand the intermediates are formed. The energy of those intermediates are different, and that'll dictate which pathway is more likely or easier to access, which gives rise to selectivity in the final product. So with that understanding, I think we can restate Markovnikov's rule. Instead of just stating what we observe empirically, we can actually use this understanding and state it in a better way that we could apply to many other cases besides just HX division. When an unsymmetrically substituted alkene reacts with an electrophile, I will say, HX, protonation or whatever is positively charged that's adding to it occurs to form the more stable carbocation. So in these reactions, you selectively form the more stable carbocation, and then the products come from that intermediate. Okay, that's a better rule to remember and an explanation of the outcomes that we observe. Okay, everybody clear on this? This point. An unsymmetrically substituted double bond, meaning there's a difference in substitution on the double bond, where in one side you might have more hydrogens, for example, and that's not symmetric. There are two alkyl groups on this side, one alkyl group on this side. Now you have a difference in which way the proton can add. Any other questions? Okay, well this can be extended to a lot of other reactions, and we can do all kinds of different reactions with double bonds, thinking about adding something positively charged first. Like in HBr addition, we added a proton to form a carbocation intermediate, and then we added Br minus. Well, we can extend that to think about adding an H plus, and then instead of adding a Br minus, you could add an OH minus in some form or another. In this case, reaction where overall the reaction produces an alcohol functional group, not a halide functional group, by the addition of water, H2O, to a double bond. Okay. Adding water, we would refer to this as a hydration reaction. For obvious reasons, water, hydration. This particular reaction is not that easy to do. You'll notice the conditions. It requires a Bronsted acid catalyst. In this case, this example is phosphoric acid. And a temperature of 250 degrees. You can take propene and add the equivalent of an H plus and an OH minus across the double bond. So I'm just going to highlight an additional hydrogen has been added to that carbon. Just like in HBr, you added an H and then a Br minus. Here we're adding an H and a OH minus overall. So how do you think this reaction takes place? Stepwise, mechanistically, what occurs? Now think about this. It's not quite the same as HBr. What is, anybody know what the pKa of water is? Huh? The pKa of water? No. The ability of what? I think you're thinking of hydronium ion where water is protonated, not H3O plus, of H2O. Yeah, the acidity of water is about, what, 16? pKa is about 16. Okay, so it's not a strong acid. So in order to get something to protonate the double bond, you need a stronger acid. And that's why this is catalyzed by phosphoric acid, or many other acids could be used. Sulfuric acid works just fine, other kinds of acids. So as long as you have some kind of acid source, the same first step can occur as occurs when we add HBr. You react the double bond with an acid. And I'll just use the phosphoric acid here as the illustration. So if you take the proton from phosphoric acid, what do you form? You form an intermediate carbocation, right? Now you can add the proton here, I'll highlight it, and then form the carbocation there. Or the other possibility is to add the hydrogen here and form the carbocation there. Which one occurs? Obviously, you can see the product, so you should know. But based on what we just talked about on stability of carbocation intermediates, we know that the secondary carbocation is favored over the primary carbocation. It's a carbon attached to two alkyl groups. This is a carbocation attached to only one alkyl group. Okay? So that first step happens. I'll just write the byproduct here. So this one doesn't form. The secondary carbocation is the one that forms. The byproduct here is H2PO4 minus. I'll just keep that in there just for clarity. Then the next step. What has to happen in the next step? Something minus has to add, right? When we had HBr, it was H plus and Br minus. When we have addition of water, under acidic conditions, we're not going to form OH minus in an acidic reaction, right? But once we have a reactive carbocation, water itself is going to react with the carbocation. So this is essentially the same as addition of HBr with an additional step that we have to take the proton off of water at the end. So the intermediate here now looks like this. Water has a 4 mole plus charge. That's not the actual final thing, because what happens is we need to regenerate the catalyst, the phosphoric acid catalyst, and go back to form the product. So this anion will take the proton, neutralize that O plus, and we'll end up with the alcohol and regenerate then our phosphoric acid catalyst. So that's what a catalyst is. Remember we defined catalyst last time too? Something that's put into a reaction to lower the activation energy, to be able to get a reaction to occur that wouldn't otherwise, but it's unchanged at the end of the reaction. So I want you to realize the similarities of the addition of water to a double bond as the addition of HX to a double bond. Okay? Essentially, the steps are the same with the additional requirement that we just have to regenerate the catalyst in the end. We add something plus, in this case an H plus, and then we add some nucleophile, something donating electrons. In this case, it happens to be neutral water, which we then have to take a proton off. Okay? This regioselectivity is the same because we're forming the same kinds of intermediate carbocations. So those are the generalities that you should recognize and be able to carry from one type of reaction to the next. Each of these reacts in similar ways, with maybe some fine little points like this last part here that are different because of what we've actually added. Okay, so that's hydration of an alkene. If you want to just remember this simply, think about water under acidic catalysis is adding the equivalent of an H plus and an OH minus across the double bond. So something plus, if I'm generic, A and B, A plus B minus would react with a double bond to form selectively the plus thing going to the less substituted side and the minus thing going to the more substituted side. Same as HX or H and OH. Just how we get it to happen varies just a little bit. Okay? Any questions on that? Well, there are other things we can add. There are many kinds of electrophiles, things that are positively charged, that we can add to a double bond. And another thing that we can add is a halogen. That is Br2 or Cl2 or I2. Fluorine is in a different whole nother category and it has its own unique reactivity. But chlorine, bromine, iodine, any of those halogens react with a double bond to add across the double bond, to add a halogen on either end of the double bond. Okay? So if you look at this overall reaction, addition of halogen to a double bond, how do you think the reaction proceeds? Why would it proceed in such a way? So if you think about what we've already learned, right? We know that double bonds are electron-rich nucleophiles. Okay, the double bond is a nucleophile. It reacts with electrophiles, something that's electron-poor, something with a weak bond. Actually, the halogen-halogen bonds are relatively weak. And as a nucleophile comes towards it, it polarizes the bond. So in this reaction, what happens is the double bond attacks the halogen and breaks this off, just like it did with HBr. Okay, it'll attack the hydrogen and bromide will leave. The same thing with Br2. It'll attack the bromine, think about it like a Br plus, kicking off a Br minus. Okay. See the similarities there? So in this case, if we're talking about halogens, bromine, chlorine, or iodine, adding, we could think about this as an equivalent of adding across the double bond in X plus and in X minus. Okay? Hence, we get a halogen on both ends of the double bond. Okay, so what do you think the mechanism is? There's an intermediate, right? So we're going to form some kind of positively charged intermediate if we add Br plus, and then we're going to add Br minus to get the second step. Okay? Well, here's where things can be a little different. So I'm going to show you some data, and we want to figure out if we can't explain it or come up with an explanation. So I told you that if you add HBr to a double bond, you get addition to the more substituted where the bromine adds. What I didn't say is that, let's say we have something like this. Let's just say a cyclic ring, okay, with a couple of substituents on it. If we add HBr to that, okay, we can form two products. Because of the ring now, we have stereoisomers, where we can have the hydrogen and bromine adding on opposite sides of the ring or on the same side of the ring. So in this case, I'll just change the bromine up. Okay. Is my drawing too messy for you? So I've added HBr to the double bond. The hydrogen adds to 1 to form a carbocation intermediate, which I will draw here. I'll draw the carbocation intermediate. Okay? Remember, carbocation is planar still. It's an sp2 hybridized. So what happens in this reaction is that the bromide in the second step could add to the bottom side or it could add to the top side. That would give the two possible products. And in fact, if you do this reaction with HBr, you get a 50-50 mixture. Or close to that. Okay? So not very selective. And it clearly shows that we have a carbocation intermediate which is planar, which has a lobe above and below. We could attack from either side with the Br minus. Okay, that's what we observe. So if we think about the addition of halogen, Br2, to the reaction instead of HBr, you might envision the similar mechanism happening where we add a Br plus, we form a carbocation intermediate, and then the Br minus would add. But if it was exactly the same, we should get also two different products. So let me just redraw this with Br2. So there's our double bond, and the products we would get from this would be possibility of the two Brs on the same side, or the Brs on opposite sides. And the methyl groups obviously switched. So the bromines could be cis or they could be trans, right? Well, I'm going to throw a monkey wrench into the whole thing now and tell you that this is the only product, the trans, and we don't see any of the cis product. so we would expect the reaction to be exactly the same as HBr. There are some differences, just slightly different. Yes, it's a two-step reaction. It forms a positively charged intermediate. What happens though is that because bromine or these halogens are larger and they also have lone pairs on them, they can directly interact with an adjacent carbocation. So if I draw this intermediate, and I'll just draw it as the carbocation for now. You see that's a plus charge. Okay? If we have this intermediate, we would expect two different stereoisomers of the product. Top and bottom addition of Br-, but we only see one. That means we're only adding bromine from the bottom for the second step. Well, it turns out that the lone pairs on bromine actually form a bond to the carbocation. The plus charge is more easily accepted on the bromine than the carbon. And I think I have this on the next slide. Oh, I even have that. Adds only one direction. And it forms actually a bridging compound. The difference between adding a proton to hydrogen versus adding a bromine is there's more lone pairs on bromine. And that allows it to, instead of having the plus charge on the carbon, it uses one of its lone pairs to form a second bond here. Okay. Because there's a second bond there, the only way the bromine can react is from the bottom side. So this is what we've found from experiment. When you have an idea of a mechanism, electrophilic addition to a double bond, and you understand how it works, then you get an unusual result. You need to think about what's different. And again, the difference between a proton and a bromine or another halogen are the lone pairs, which allows this kind of intermediate to form, which blocks the top phase. So this is the only pathway for the bromide, allowing then that bond to break again. And add those on opposite sides. So the stereochemistry of addition of Br2 is selective. It's specific. We call that a stereospecific reaction. Whereas the addition of HBr would not be selective. And it's just because the nature and structure of the carbocation or plus charged intermediate is a little bit different.
Why is it a stereo?
Why is it a stereoisomer? The other product would be the trans. I'm sorry, the other
Why is it selective?
It's selective because of this bond where we would have had a carbocation, it's blocking the top. So this can't happen.
Okay.
So the bromines can't add on the same side, they have to be on opposite sides. I mean, we see this where it really matters is in rings and things like that where we can actually see the stereochemistry. Obviously, if you're forming a linear alkane with two bromines, there's free rotation, you wouldn't see any difference. But it still forms the same kind of free-membered ring intermediate with the halogen. Iodine does this, chlorine does this, bromine does this. So the ultimate consequence is we have to know that it's a specific reaction also in terms of the stereochemistry of addition. It's selective for one forming the trans addition over the cis.
So what if it was, you're adding, Br2 to like pentene?
Yeah, so if you're adding Br2 to pentene, like this, right?
Yeah.
So in actuality, if you add Br2 to pentene, you still get the same intermediate that's bridging. I mean, you still form this where the double bond was. And then the Br minus that's left over will react on the opposite side. But because the product is just a linear chain, there is no stereochemistry associated with it because there's free rotation. So you don't see the result. You only see it when it actually has the possibility of forming two different products. that are stereoisomers. Does that help?
Yeah.
By the way, if you think about this reaction, we can add Br2 to a double bond to form a dibromide compound. Okay, and it's selective and things like that. We form a carbocation or a bromonium intermediate. And we should be able to extend this reaction. And I don't think your book talks about this reaction, so just for your information, think about, with this knowledge, what we could think about doing next. If you were to carry out this reaction with Br2, instead of in some inert solvent, if you did it in water, what do you think would happen? Something like this. We can envision this. So this is why understanding how the reactions take place allows us to think about doing new things with it to form new kinds of products. So in fact, you can take bromine, and if you just do the reaction in water, there's a possibility in the second step, instead of Br minus reacting, the water could add, just like we did before with hydration, in forming a alcohol in the end. So in this case, we can add a Br and an OH across a double bond. Or you think about when you become more familiar with other types of functional groups which are nucleophiles, you can think about making all kinds of different things from this. Okay, so just for your information, this is how we think as chemists. If Br minus adds, well, what else can we add? Or what else can we intercept that intermediate with to make new things? Okay. So I've generalized here this sort of concept overall for electrophilic addition to a double bond and how it might be easier to think about it when you see a set of reactants reacting with a double bond. Now, some of these you haven't seen before. For example, we didn't talk about borane, so don't worry about that. But in general, if you think about a double bond as being a nucleophile, adding something plus to it to form some plus charged intermediate, that's what I've shown here, and then adding something minus is the second step. There are things you should generalize. If it has the possibility, like halogens undergo bridging, but selectivity for regio positions matters because the most stable carbocation in all these cases. So in general, A, whatever is plus, adds to the less substituted carbon, and whatever is minus adds to the more substituted carbon. Okay? Whether that be an H and Cl, or an H and an OH from water, you get the same result. You could add a Br and another Br with the point that stereochemistry matters. That's why I put your anti-addition. Or as I showed you, we could extend that to things like Br plus and water, or OH minus, technically, as the minus group. Okay, so again, if you think about these generalities for electrophilic addition reactions, it can help you predict things that you haven't seen before. Okay, this is a reaction that we introduced briefly in the last chapter, and that is addition of hydrogen across a double bond. And as we were talking about the nature of catalysts, that's where we brought this particular reaction up in context. This is a little different than an electrophilic addition reaction because we're not adding H plus and H minus, technically. We're actually using a catalyst to template everything in this reaction. So recall, we talked about the addition of hydrogen across a double bond requires something to break apart the hydrogen because that's the real energy intensive part of that reaction. We need to find a way to break apart the hydrogen. And we use a catalyst to do that. Often, those are transition metals in their zero oxidation state. So here, for example, I've shown palladium, PD is palladium, I've just illustrated with one atom of palladium. It's actually a lot of palladium clusters. Usually embedded on some solid support like carbon or silica or carbonate or something like that to hold the metal. It helps break apart the hydrogen and then deliver that to a double bond. Mechanistically, it's a little bit complicated in thinking about all the d orbitals on palladium and all that, so we're not going to really go into that. But what I want you to recognize is that in a way, we're adding hydrogen to a double bond in a controlled fashion. We can reduce the double bond in this way from an alkene to an alkane using a catalyst like palladium. Other catalysts that do this kind of reaction, there are many of them. Palladium is one of the more common ones, but things like platinum, nickel, rhodium, ruthenium, a lot of these transition metals allow us to do this kind of reaction to catalyze hydrogen's addition to a double bond. Not surprisingly, it's called hydrogenation, because we're adding hydrogen. Hydrogenation. This is another reaction which has allowed us to characterize various differences between alkenes. If you recall a couple of chapters ago, we talked about combustion and how heat of reaction can tell us relative energy differences between molecules. If we have the same number of atoms in there, we could tell differences in energies of isomers. Well, the same is true for this reaction. If we could take a molecule which contains a double bond, like butene here, and hydrogenate it, we can see the difference in energy. How much heat of hydration, how much heat that reaction produced or consumed. Compare that to isomers of butene. We can see that the starting energy is different. This is another reaction which has been used to characterize and get properties of molecules of their relative energies. So just for your information, we can do that by comparing directly heats of hydration or hydrogenation. Okay, if you're interested about some other details of this reaction, which you should be, this is also a very stereospecific reaction. So in a molecule like this cyclic alkene that I've shown here, there is a difference between adding those hydrogens on the same side or adding them on opposite sides of the ring. Okay, what we call a syn addition, or to give the cis product, or an anti-addition to give the trans product. And with this reaction, it forms selectively only one product, where the two hydrogens add on the same size. Okay, and that's because the catalyst is templating all of that. Because both of the hydrogens are on the metal, it's putting both of the hydrogens on the same side of where the double bond was. Okay, I think I have a little more detail here. This is again a sort of a pictorial schematic representation that kind of just shows the surface of a metal catalyst. This is actually what's been determined to happen. As I said, hydrogen gets broken up, the hydrogen-hydrogen bonds. So when you put this catalyst in the alkene and a hydrogen atmosphere, the hydrogen gets absorbed on the surface of the catalyst. It breaks apart. I've just shown a little bit larger view of that. There are hydrogens, essentially metal hydrogen bonds, which have been formed around the catalyst. The alkene comes in, then the alkene binds to the catalyst, and then they start delivering the hydrogens to the carbons that were originally the alkene. But because it's attached to this catalyst, it's delivered specifically in one side. And that allows us to do a reaction which gives us the cis hydrogens on a double bond where that matters. Again, if it's a linear alkene, you hydrogenate it, you just form an alkane which freely rotates. You don't see the result of that because there is no stereochemical difference between the possible products. But it still is selective going in this particular manner. So there's another reaction we can do with double bonds. We can reduce them. We can get rid of them. Okay, pretty neat, huh?
I think so.
You might not, but I think so. Now, when you have larger molecules, I'm showing this example of a hydrogenation of a molecule which is a little bit larger because it illustrates another point that reaction pathways that could produce multiple stereoisomers depends a lot on sterics, the crowding around the reaction sites. So, for example, this is a naturally occurring molecule called alpha-pinene. It has a difference in the top part of the ring versus the bottom part of the ring. So, on the top part of the ring, we have this group sticking up here. We have an alkene that we want to do a reaction with. And we do a hydrogenation with a nickel catalyst for this reaction. We observe the formation of the hydrogenated product where the hydrogens add to the same side of the ring, but now there are two different possibilities for that. Here, the hydrogens added to the bottom. These are cis hydrogens, okay? They added to the bottom. Here, the hydrogens both added to the top, okay? The hydrogens are on the same side. We call it trans because this group has changed. So don't be confused by the name. Now we're talking about which side we do the reaction on, and is there selectivity? Well, the crowding on one side is going to be different than the other. So what's observed in this reaction is that the cis-pinene product where the hydrogen is added to the bottom side is the only one formed. And that's because the top part is a little bit better drawing. The top part is being blocked. Okay, there it's back. The top part is being blocked, and remember, we have this metal surface that's the catalyst for this reaction. There's no way it can fit here because this part is blocking. So the only place that metal surface could fit is on the bottom side to deliver the hydrogens here. So there are other ways we can think about having selective reactions using steric differences on one side of a molecule versus another. And that helps us control things. Okay, so hydrogenation is another reaction. I want to talk a little bit about the concepts of oxidation and reduction. When I talked about hydrogenation, I said we can do a reduction of a double bond. Okay? And that might have went past some of you. What does reduction mean? What does oxidation mean? We know what oxidation and reduction are in terms of our atoms and elements, right? You have, for example, on the left side of the periodic table, you have lithium metal, lithium atom. If it gives up an electron, it becomes oxidized to a lithium plus, right? That's an obvious change in the oxidation state of that element because it's actually gone from lithium with one electron to lithium where that electron is gone, and now it's positively charged ion. Okay, so it's in a +1 oxidation state. That's easy to see oxidation, and the reverse of that, reduction, gaining electrons, when we're talking about ions and elements. Okay, but what does it mean to say we've changed oxidation states of carbon in molecules which are all covalently bonded? Okay, it's a little bit more of a gray area because we don't see what is the oxidation state. We don't think about those molecules necessarily as being single unit oxidation states because in covalent bonds, there's a whole range of polarizations of bonds. So what atom owns the electrons when you start counting oxidation states? It's harder to describe and say that in molecules with covalent bonds, like organic molecules. So we think about oxidation and reduction of organic molecules in a little bit different way. as opposed to just oxidation states. I mean, technically, if you were to count and try to assign electrons to more and less electronegative atoms, methane would have a carbon oxidation of -4. If you think about carbon, if you think about the hydrogens as owning the electrons from each of those bonds, being more electronegative than carbon. As opposed to carbon dioxide on the right, if you think about, I'm sorry, the other way around. Carbon owning the electrons, hydrogen less electronegative. Oxygen's on the right, 4 bonds to oxygen, then you would say oxygen is more electronegative, it owns all the electrons. Carbon must be in a +4 oxidation state. But it's, again, because it's covalently bonded and the electrons are shared, it's harder to talk about oxidation reduction. So we define it a little bit differently. We talk about the oxidation of carbon as increasing the number of bonds to a more electronegative atom. Typically oxygen, but it could be other atoms. When we think about what is more or less oxidized form of carbon, the more bonds to oxygen, the higher oxidation state it is. Okay, the less bonds to oxygen, comparing molecules, the less oxidized, or the more reduced it is. Okay? Reduction is the opposite of oxidation, and again, it's about electron ownership, and so we think about how much, an electronegative atom is pulling more on the electrons in a covalent bond, so they kind of own the electrons more, if you will. And so when we think about oxidations, I like this first definition, increase the number of bonds to more electronegative atoms. So you compare a molecule, whether it's oxidized from an original one. Have you replaced a CH with a CO? Have you replaced a CH with a carbon-bromine bond? Those kinds of things. That would be an oxidation, and the reverse would be a reduction. Hydrogenation of a double bond, to add hydrogen across it, that's a reduction because we think about hydrogen as being less electronegative than carbon. So we've replaced a carbon-carbon bond, the pi bond, with carbon-hydrogen bonds. That's why we call that a reduction. So here's sort of some examples of molecules that we would say would be different in oxidation states of carbon, higher oxidation to the right. So in all these examples, for the ones all the way on the right, you'll notice that the carbons all have 4 bonds to more electronegative atoms, and we would say these are all like the same oxidation state of carbon. But if you compare like carbon tetrachloride here, the oxidation state of that versus methanol, okay, we can clearly see that this has 4 bonds to more electronegative atoms, and this only has 1 bond to a more electronegative atom, and more hydrogens on it. So this is in a lower oxidation state than carbon tetrachloride, right? Because we've reduced the number of bonds going from there to there. That would be a reduction going from CCl4 to methanol, if that reaction was possible. And if we're going from here to here, or methanol to carbon dioxide, or methanol to carbonic acid, those are all oxidation reactions. The oxidation of carbon is increased. Okay. Going from carbon, let me just clean this up. If you go from like carbon dichloromethane to formaldehyde, we haven't really increased oxidation because we still only have 2 bonds to more electronegative atoms. So you see how we think about a little bit more, if we define oxidation reduction this way, it makes it a little bit easier to see a reaction and whether it's been oxidized or reduced. Okay, any questions on that? Well, oxidation is sometimes a good thing because we can impart functional groups into molecules that we can do different things with by doing oxidations. We talked about oxidations of alkanes, right? When we burn an alkane, what happens? You burn methane, you end up forming carbon dioxide and water. because you have to burn it in oxygen. So we've oxidized methane to carbon dioxide and water. More oxidized compounds often have oxygens in their functional groups, and there are a variety of them. We see all kinds of different oxygen-containing functional groups, and these are the ones that are just single-bonded oxygens to carbons. Of course, one could have something like water, but if you replace one of the hydrogens of water with a carbon group, some organic group, now we have a functional group called an alcohol. Okay, many kinds of alcohols, but it's the OH group attached to a carbon which defines alcohol. Okay. If the second hydrogen is replaced with another carbon, if we have carbons on both sides of the oxygen singly bonded, we refer to that as an ether. The generic word ether, anybody know what molecule that stands for? When we say ether, there's a particular ether molecule that it refers to. So the old-time anesthetic, if we have modern anesthetics, they used to have people breathe ether to knock them out. And that molecule was this one, diethyl ether. So when you refer to that old anesthetic ether, it's diethyl ether. But you can imagine there are an infinite number of ethers possible because you could have all kinds of different carbon groups. A very special kind of ether is one in which the two carbons of the oxygen is in a ring, in particular a three-membered ring. This is what we call an epoxide. An epoxide. So epoxide has some interesting reactivities, which I think we might see in a future chapter. I'll have to take a look. And they are very useful for synthetic chemistry because we can do a lot of different kinds of reactions with them. Because of the strain energy of the ring, we can add other groups and open it up and things like that. But the epoxides, being important for intermediates in various multi-step synthesis, we would like to have good ways to make it. Unfortunately, they're made very easily from alkenes. That's why we're talking about it in this chapter. Reaction of alkene with some reagents to put oxygen in is an oxidation reaction. In particular, there's a reaction where we can insert oxygen using what we call a peroxy acid. So people are familiar with peroxide. A peroxide, the general term peroxide refers to anything with an oxygen-oxygen bond. That's a really weak reactive bond and does lots of oxidation reactions. And fortunately for us, these molecules that have an oxygen-oxygen bond, a peroxy bond next to a carbonyl group, is something we refer to as a peroxy acid. These will give up one of these oxygens and insert it into a double bond. Mechanistically, it happens all in one step, kind of depicted by this transition state. It's not important that you understand and be able to regurgitate the picture of this transition state, but I want to point out how it's happening so you can understand that one of the oxygens from the per acid reacts on both ends of the double bond simultaneously to form the three-membered ring, and what's left is the group without that oxygen. Okay, so peroxy acids. Peroxy acids, there are several of them. I guess I should say the simplest one is peracetic acid. It's commonly used. Your book refers to this acid. Per, referring to peroxy. Peracetic acid, because the two-carbon carboxylic acid is acetic acid. Peracetic acid is the one where that's just a CH3 group. One that's very commonly used in organic chemistry is abbreviated MCPBA. So you might see me use this abbreviation. If you're interested in the structure, it looks like this. It's a little bit more complicated than peracetic acid, but tends to be a little more reactive, and that's why we use it a lot. And it's a solid too, so we can easily weigh it out and utilize it practically. So that's what MCPBA stands for. Metachloropurbenzoic acid is the name for that. But what you should recognize is that the reactivity of a per acid, regardless of what kind of per acid it is to insert an oxygen into a double bond. And so if we take a alkene like cyclohexene, react it with a per acid, a peroxy acid, we form these epoxides. And one of the reactions we can do with peroxides is to add water to that and open it to form a diol. This is another useful functional group. So the nice thing about making these intermediates is we can do all kinds of things with it. So this is a good method, a good tool for us to be able to make diols, particularly trans diols, if you have it on a ring. Okay, that happens to be selective as well. Which begs a question, why do you think, and how do you think this reaction, adding water with an acid catalyst, adding water to an epoxide to open it up and form a diol, how do you think that's happening? Do you see anything similar to things we've talked about before?
The oxygen be reaching for the hydrogen.
Yeah, the oxygen will be reaching for the hydrogen, so we protonate the oxygen to make it more reactive. But the structure, three-membered ring, is similar to that bromonium intermediate, where Br minus added on the opposite side, right? So there are similarities here too, although it might not have been easily recognized. I'll just draw, first of all, acid catalyst. You transfer the proton from the oxygen of the water, H3O plus, to the oxygen of the per acid. I'm sorry, the epoxide. Okay, that leaves behind water. Now, by doing this, what happens is now with oxygen here having a plus charge on the epoxide structure, those bonds are weakened. Now it's more reactive. Water will react just like it would react with a bromonium ion. It'll react with this protonated epoxide to come from the opposite side and then break one of the CO bonds. And that forms the product after the acid catalyst is regenerated. So that last step, a proton has to come off and regenerate the acid catalyst that started the whole thing, which I've kind of neglected in the arrow. So, there are similarities there too. The structure of an epoxide, it's less reactive than an intermediate bromonium, but we can do similar things if we activate it in the right way. Yes, question?
What exactly is a diol?
A diol is a molecule with two alcohol groups. So you see we have two OH groups. That's a diol. And 1,2-diol means they're next to adjacent carbons. So this is trans cyclohexane 1,2-diol is the name of that molecule. And when we get to the alcohols chapter, we'll talk more about the naming for those then. This is very useful, again, as I said, as a synthetic tool. So the next question we would want as a synthetic chemist, if I have a tool to take cyclohexene and make a diol which is trans, is there a tool that I can selectively take cyclohexene and make a diol which is cis? How do I make that molecule? That's the question that as chemists we say, we need the tools to build molecules, we need to be able to have the tools to make all the different kinds of molecules we want and control it. Fortunately, there is a reagent, an oxidation reagent, which can do this directly. And it is potassium permanganate. This is another oxidation of an alkene that delivers two oxygens to the same side of a double bond. Under basic conditions, it tempers the reactivity, so it stops at this stage where we have two OH groups added. If we do this under acidic conditions, it actually is too strong of an oxidizing agent. It actually breaks the double bond completely and adds an additional bond to oxygen to make two double bonded oxygens on the ends. Okay, and if you force this reaction, you go all the way to a third oxygen bond, and you could, for example, if you heat that one up, you would go to that molecule, where we added a third oxygen bond. We've even oxidized all the CH bonds on the molecule. Okay, so oxidation reagents like potassium permanganate, it's a very strong oxidizer. Allows us to make diols under the right conditions or dicarbonyls, break apart double bonds completely. If it's not in a ring, then you'll form two different molecules. If it's in a ring, you just have the two double bond oxygens on either end. So some things to think about in terms of specific structures. Okay, I think I'm going to stop there today. We'll talk a little bit more about oxidations and some other reactions of alkenes on Tuesday. Have a great weekend. We'll see you next week.